Hey everyone, welcome to this episode of This is Automation. I'm Corey Dallas, your host. Today we're going to be talking about OPC UA TSN. Many of you may not even know what that is, but we'll talk all about OPC UA, the OPC Foundation, what is TSN, how do you use this technology, and a little bit of the history of the technology, kind of why we even need this. So to do that, I'm going to set the scenes, go back to the 1990s. I pulled up the Wikipedia page for the 90s and I was reliving some moments. So, think back, the highest grossing films of the 1990s, Titanic, Star Wars Episode 1, The Phantom Menace, arguably the best Star Wars movie of all time. Jurassic Park, Independence Day. Will Smith is in his prime. Pulp Fiction, there's so many good things happening in the 90s. Mariah Carey, Nirvana, Spice Girls, Dr. Dre, lots of really good music being made. We've got amazing TV, Roseanne, Friends. We got lots of really, really, really good things happening in the 90s. But there was some bad things happening in the 90s too, besides the fashion and all sorts of other things. But one of the worst things that happened in the 90s is the fieldbus wars. And the fieldbus wars are still raging on now today. We're getting close to a peace treaty. But if you don't know what the fieldbus wars are, we're going to talk all about that. But go get your Sony Walkman, pump some Mariah Carey, go watch The Phantom Menace, get in the 1990s zone, and then come back right after this short break. Welcome back, everyone. I hope you enjoyed the little trip down memory lane into the 1990s. And now let's talk about the fieldbus wars. So before we even talk about the fieldbus wars, we should probably address what a fieldbus is in general. So a fieldbus, kind of simply put, is basically a communication protocol that's specifically designed for the automation industry. So typically, these have extensions for real-time communication, but that's not necessarily true. They don't always. Some of the biggest ones actually don't have that. But in most cases, they will have that. The fieldbus was originally designed to replace these traditional 4 to 20 milliamp communication schemes and some other types of networks as well. Because a fieldbus can basically theoretically connect every device on the network with a single set of wires, the complexity of these old 4 to 20 milliamp networks could be really drastically reduced. So instead of having a dedicated set of cables to each parameter that you needed to transmit all over the place, basically with a fieldbus, you can send multiple parameters and diagnostics information and other information across a single set of cables. So cost and complexity obviously get drastically reduced with that. And obviously the capability of automation systems is greatly enhanced with the fieldbus. So it stuck. Now, usually when things stick, they start to build standards around that. And that's exactly what happened with the fieldbus. So the first standard that defined a fieldbus was ISA, which is the International Society of Automation. We don't really use that standard anymore. That happened in 1988. About a decade later, in the 90s, the IEC released IEC 61158, which I'm sure those of you in the automation industry, that rings a bell. So that's one that we still use today. The initial release of 61158 included 8 different protocol types, is what they called them. Later releases kept introducing more and more and more protocols, and you'll see this is kind of part of the problem, why we ended up in the fieldbus wars and why we're in the situation we are today, where there's so many field buses out there and it's really complicated to communicate between different systems. So, some of those protocols, just to give an example, you've got things like SIP, Profibus, HART, EtherCAT, Ethernet PowerLink, Modbus, Circos, so on and so forth. The 2008 release, based on my research, had 16 different protocols that they called communication profile families. So at some point they changed it from types to these CPFs. So 16 different field buses that are considered standards. So this is it creates a lot of challenges in automation systems still today. So, it's nice on one hand because virtually every major automation supplier in their field bus is well represented in the standard. So that's good for all of these different vendors. But the problem is there's 16 different field buses that are the standard. So it's really not much of an industry standard. And there's actually a reason behind this. It's really interesting. So we'll talk about that for just a second and then kind of move forward to the conversation on OPC. But basically, the IEC made a really intentional decision to do this, to include all these different field buses. So it's not really a mistake. They weren't just being foolish and saying, yes, and you get a standard, and you get a standard, and you get a standard. But that's what happened. And the reason why is the kind of the traditional focus of standards is all about the user. It's supposed to make it easier for the user of the technology to implement that technology and to access it across multiple applications. That's why we have standards. So for example, in your car, the gas pedal being on the right-hand side is a standard so that as a user, any car that you get into is easy to understand how to operate. If every automotive manufacturer could put it on the left or the middle if you drive a clutch, it would be really, really hard to drive cars as a user, while it may be more cost effective or something for the automotive manufacturer to have freedom over that design. By having a standard in place, we're giving a lot of power to the user and taking some of the design freedom away from the automotive manufacturers in that case. But ultimately, it benefits everybody because we have that standard in place. So that's the traditional focus of standards. And if we look at more of a automotive or a automation focused example, let's take the 4 to 20 milliamp standard. So we're all very familiar with it, with the 4 to 20 standard. Let's say instead of just one 4 to 20 or 0 to 20, maybe two, you can make the argument. Let's say there was a 4 to 20, 10 to 50, 20 to 60, 3 to 15, and then add, 12 others to kind of get yourself on the level of how many field buses there are in IEC 61158. It would kind of be a nightmare, and it is kind of a nightmare to manage these field buses. So anyways, back to why the IEC did this. When they legitimized all of these different field buses in their standard, basically, in the 90s, we need to look at what actually had just been renamed the European Union. So the European Union had basically embarked on this effort, as a part of its, newly founded identity to, harmonize all of the member states of the EU. And part of that included standards. Testing and certification requirements, reasonably so. As an entity, the European Union could operate much more cohesively and have, much more open trade and harmonization of markets if they were operating on the same standards. So to support that harmonization, basically the European Union Single Market Program is what it was called, was established in 1993. And the goal of this program was explicitly to allow goods, services, capital, and people to flow more freely throughout the EU by reducing or eliminating differing requirements and standards among the member states. So the explicit goal of this single market program was to take down as many barriers to trade between the member states as possible, to the flow of goods, services, capital, and people. Okay, so again, seems like a good thing for harmonizing the EU, but the result of this program is that the kind of underlying goals of standardization itself and these certification requirements kind of changed for the organizations that were tied to the EU, which included the IEC and ISO and several other kind of standards organizations. So prior to the onset of the single market program, international standards were defined to benefit the user, as we were just talking about. However, in the interest of reducing trade barriers for the member states of the EU, the benefit of the user was kind of pushed to the side. And this is really the reason why all of these different field buses started being implemented in this way. So because of the single market program in the EU, and because these standards organizations had ties to that kind of new standardization ideology, standards started to be implemented in this way where it was less about focusing on what's best for the user from a standardization perspective, and more about how do we reduce the barriers to trade, reduce the barriers to technology for not just the member states of the EU, but around the world. And the easiest way to do that is standardize all the field buses. Because if we standardize all the field buses, then all these different countries can make their automation systems work together, right? So it's a nice idea, but basically it kind of set in stone this mess of field buses that we're still kind of fighting through today. And if you look now, fast forward to 2018, so go through your Sony Walkman and Mariah Carey CD and the garbage can. It's 2018, 2019. We're living in the modern age, but unfortunately we're still stuck with this IEC 61158 standard, with these 16 different field buses. And now there's somewhere on the order of like 100 different field buses that you could pick from, outside of the ones in 61158. So it's really a huge mess, and it's really cumbersome for people working on automation systems to work through. So how do you pick which field bus is the right one for your application? And if you're being forced into a specific field bus because of a hardware spec, or because you're using a hardware from a specific manufacturer, but then you've got another system that uses something else, like how do you handle that? And the answer is it takes a lot of software effort and a lot of money and sometimes hardware to do all these handshakes, and you end up with a lot of latency in your systems because of delays in the network time as it goes through all of these different field buses. And it's really not a very cohesive, integrated type solution for automation, especially as we move more towards these highly synchronized, really time-sensitive applications where network times, where milliseconds or things on the order of milliseconds was not an issue maybe 10 years ago. In some cases it was, but now it's becoming more and more an issue as we try to squeeze performance out of our machines in every way possible. So we've got this mess. How do we clean it up? The answer is kind of more simple than you might think. We just take all those and kind of throw them away and move to a new standard. So that's what OPC UA is all about. So OPC UA is a single standardized field bus communication that is structured to basically end the field bus wars. So OPC UA is so well designed that not just me, but actually a large number of automation companies think that it will not only end the field bus wars, but it will kind of wipe the slate clean for industrial communication protocols. And basically because it's got all this interoperability and user benefits, at its core, the core of the technology, it's really ideal for automation, and everyone's kind of getting on board with this technology, especially with the implementation of TSN, which we'll talk about what that is. So kind of what we're expecting, in an ideal world, of course, this will happen, but, over time, OPC UA will replace every industrial field bus as the standard industrial communication protocol. So, in a short few years, PLC brand A and PLC brand B, which used to have two different communication protocols, will likely have OPC UA at least as an option so that you can communicate freely between those two, and you don't need to buy any third-party hardware or implement complicated communications libraries just to send data back and forth, on a line or, at the field level or at the cloud level. It's going to be a really fully fledged solution that handles all of those different use cases. So now that we understand the field bus wars and a little bit of the history of why we need a standard industrial field bus like OPC UA, let's take a look at where OPC UA came from and what the OPC Foundation is all about. So OPC UA is actually the kind of second iteration or second generation of the OPC standard. So the OPC standard itself was first released in 1996. which you'll notice it's kind of ironically right in the time when IEC 61158 was being released. But basically, it was originally designed as a way to abstract PLC-specific protocols into a standardized interface to allow simple communication with HMIs and SCADA systems. So it wasn't really originally designed to be a universal communication protocol for PLC to PLC communication or field device to PLC communication or, plant level communication or cloud level communication. It wasn't really designed for any of that. It was just designed to be used as an interface between any PLC and, HMIs and SCADA systems. So OPC was originally restricted to Windows, which is where it gets its name. So OPC actually stands for Object Linking and Embedding for Process Control. So OPC. So it's got an acronym within an acronym, which are the best kinds of acronyms. So the original specifications of OPC, which I just described, are called OPC Classic now. So basically, as time went on, the OPC standard couldn't really meet the security and data modeling needs of the industry. So OPC Unified Architecture was released. It's a standard based on OPC Classic, but it addressed all of these kind of new concerns that were coming up in the industry to develop a future-proof platform for industrial communication. So OPC UA, like I just said, it takes the functionality of OPC Classic and adds a whole bunch more capability. So you've got things like server discovery, subscription, server-defined methods, platform independence, security, advanced information modeling, so on and so forth. And the really, really beautiful part about OPC UA is that this is all built on an extensible framework, which means that the OPC UA standard that is out now can implement new transport protocols. It can implement new security algorithms. It can implement new encoding standards. It can, do all these things basically to improve the standard and keep it up to date with all of the latest security and protocol enhancements, while maintaining backwards compatibility with the existing implementations of OPC UA. So that's super, super powerful. So you don't really have to worry about, but what if this, changes, security is a big topic now. So I don't really want to use this OPC UA stuff because, the security stuff's all going to change. We're just going to keep using Ethernet IP and then do all this hacky, communication protocol conversion. You don't have to worry about that because OPC UA has been really, really well designed to make sure that they can implement all these sorts of changes while maintaining compatibility with systems that are built on OPC UA of today. So we're only kind of halfway through the acronym of OPC UA TSN. So the TSN part of it is time-sensitive networking, and it's kind of the exact same evolution that happened from OPC to OPC UA. So OPC UA, great. It's been around for a little bit now, and there's some applications that use it, but it doesn't have real-time capabilities. So it's a big kind of weakness of OPC UA. So OPC UA implemented over TSN is going to, allegedly, it has solved that issue. So TSN, again, time-sensitive networking, is an extension of the IEEE, which is the Institute of Electrical and Electronics Engineers, if you don't happen to know that, but the IEEE 802 Ethernet standard. So TSN basically allows for determinism over networks that are defined within IEEE 802, which is kind of a mouthful. But basically, all you need to know is that it is a way for a standard way for networks to have determinism over standard Ethernet. And so when we say determinism, well, what does that mean? In this case, it basically implies guaranteed packet transport with bounded low latency, low packet delay variation, and low packet loss. Okay, so by implementing OPC UA over TSN, we get all of the benefits of OPC UA, which we touched on lightly, being things like security, built-in user roles, built-in units, standard data modeling, so on and so forth, security, extensible framework, all this really, really powerful stuff. And it's all still accessible, but now you get the benefit of determinism. So this is where OPC UA is really, really becoming powerful, is now we've got this awesome, well-designed protocol that's available in a deterministic way. So this is huge for industrial automation companies, and this is why you've got companies like B&R, like Rockwell, like Siemens, like Mitsubishi, like Beckhoff, all getting on board the OPC UA TSN Shapers Group. So the Shapers Group is basically a group of industrial automation companies that are helping to define the OPC UA TSN product or standard. And so you could reasonably draw the conclusion that all of these companies are planning to implement OPC UA TSN into their products, and that is happening. At some trade shows and such already, they've started to display some of the capabilities of this system, and it's really, really impressive. So as we continue to forge ahead into modern industrial automation, where things like intersystem connectivity and IIoT are really, really important, the need to move away from this mess of field buses is becoming more and more important. And what we need is a unifying communication protocol, and we need it really bad, to be honest. So OPC UA TSN is now making that possible. We finally have a standard that is good enough, that is open enough, that is agnostic enough, that is secure enough to do that, to be the standard that Rockwell is willing to get on board with it, that B&R is willing to get on board with it, that Siemens is willing to get on board with it. So, and that's just a small list, to be honest with you. Virtually every major player in automation is on board with this technology. So you can more or less argue that the fieldbus wars are pretty much over, and 100% interoperability between platforms is not that far away, which is really, really awesome. So what we're expecting to see in the future is really exciting. But before we talk about that, let's take a very short break, and I'll be right back. The OPC Foundation basically has made it clear what its initial priorities will be. So the first one is multi-vendor controller-to-controller integration, which means communicating between two different controllers across different platforms. And then the other thing is vertical communication from field devices to upper levels. So again, it's pretty self-explanatory. That's communication from a field level device into upper levels, whatever level that may be. So that's really promising that those are the two initial focuses, because those are kind of the biggest gaps in the technology that we have today. We don't really have excellent ways to communicate between different vendors' controllers. There are ways, don't get me wrong, but there's not really any good integrated ways. So to have this be a priority is really strong. And then, on the flip side, to have vertical communication as another focus, that's going to help with things like IoT, which is a buzzword that gets everybody really excited. There's currently, from what I saw, at least 3 major test beds that are currently active that include companies like B&R, like Rockwell, like Siemens, so on and so forth. And the work groups and steering committees that are not only the OPC Foundation, but also industrial automation companies are basically shaping the direction of the OPC UA TSN standard and its implementation. So what does the future with OPC UA TSN look like? Well, basically due to the consistency of the information models that OPC UA is built on for I/O, for motion control, safety, etc., there's going to be really, really good interoperability between different automation systems. So it's not just, the same communication protocol, like as far as they're speaking the same language, but they're also structuring their data in the same way, which is huge. This is super, super powerful. So, it's not just opening that channel of communication, but it's having a structured way to communicate between, these multiple vendors and into the cloud and so on and so forth. So again, I/O, motion control, safety, so on and so forth, all have standard data models that are built around them that can be implemented on multiple vendors, so that you can share this data in a really standard way. This is huge, huge, huge. The other thing is basically the days of, communication gateways, these kind of little devices that you put in your cabinet for the purpose of protocol conversion. These special pieces of hardware that just translate field buses. That's all they do. That's going to be a thing of the past. honestly. So, and then on the flip side, if you've got a PLC that's smart enough to handle it, a lot of PLCs have communication libraries that can just do this in software with, the Ethernet port on the PLC. You're not going to have to deal with those libraries anymore. So all these kind of confusing libraries where you've got to, open and close communications with different clients and so on and so forth. You don't have to even worry about that anymore. So that's also really nice. So it's going to make development time way, way faster, especially for people that are dealing with, multi-vendor solution. You're also no longer going to have to, play the balancing act of which field bus to use to get optimal performance, in this scenario, or, market support for field level devices, or to meet end user specs. Hopefully we're going to see all of that kind of shift towards OPC UA TSN, where you're not going to have to make that decision when it's like, well, we use, Ethernet PowerLink, for example, for all of our motion control because it's really awesome at motion control. But, we want to use EtherCAT because there's a sensor that has EtherCAT built in. You don't have to make that decision or make the, even less favorable decision of, well, we're going to use Ethernet PowerLink for our servo drives and EtherCAT for this one sensor. So then we'll just have a communication protocol conversion and it's going to be awesome. So you don't have to worry about that, thankfully. So you don't really have to play that game of, we like this field bus because of this and this one because of this, and maybe we'll use this one here. And you've got all these different tools to implement them, and it's very confusing and hard to manage. It's all going to be OPC UA TSN, hopefully not too much longer. So the other thing that's huge, especially for those of you that are servicing machines or working, at the end user, actually using machines, is connecting to and diagnosing systems is going to be much, much simpler. So again, it's going to be not just you can plug in and talk to it. That's one side of it. But when you plug into PLC brand A and PLC brand B and C and D, they're not only going to have that same channel of communication open, but it's going to be structured in a common way, which is huge. So you're not going to need to get training on EtherCAT and Ethernet PowerLink and Ethernet IP and Profinet, and have maybe a specialist for each of those and all your different tools that you use to collect the data, or so on and so forth, just to diagnose or connect to your system. You're going to be able to do this in a standard way across platforms. This is huge. So we're talking about seriously reduced service costs, seriously reduced training costs, maintenance, so on and so forth. It's the cost of maintaining machinery is going to go way down because of this, and the simplicity is going to go way up. Okay. On the performance side of things, network stations basically are from tests that we have now. The standard's not out yet, but the tests that we have in place now can communicate up to 18 times faster than anything on the market today. 18 times faster. So this means like really new possibilities can be opened up for applications, or where we're hosting the PLC in a facility, or if it's being hosted in the cloud or something like that. I don't know if that's going to happen, but when you have 18 times faster than the fastest protocol in the market today, it's really fast. So you can do a lot of really creative things, and things that need a lot of speed, like highly synchronized motion applications, or highly synchronized control of some sorts. We're going to be able to push our machines to that next level from a network time perspective. So that's another huge thing. 18 times, like that's really fast. And then again, on the performance side, so OPC UA TSN supports networks with tens of thousands of nodes. So this is pretty good. It's more than most applications would ever need. But basically, it's based on the Ethernet standard, like a lot of field buses are. And it benefits from some bandwidth extensions because of that. And you're not going to have any trouble communicating large volumes of data either. So that means that as we move towards IIoT, machine vision applications, machine learning, AI, where there's lots of data being passed back and forth, you don't really have a challenge to implement that anymore. You've got a really nice standard protocol that you can use, at the field level, PLC level, plant level, cloud level. And it's going to be capable of not only running your controller, communicating to your servo drives, communicating to your remote I/O, communicating from machine A to machine B, communicating from line A to line B, communicating to your SCADA system, communicating to the cloud. But it's going to be able to enable you to do new things with all of those communications. So those new things being really creative IIoT applications, really creative applications where previously, data bandwidth was a constriction. Okay, so those are kind of just a short list. Those are the most important ones of some of the benefits of OPC UA TSN and kind of what you can expect the future to look like as far as how the implementation of automation systems is going to change with this technology. So we'll take a short break and then close up the episode right after this. All right, so OPC UA TSN it sounds amazing, right? But it's going to resolve a lot of the pain that has been present in the automation market, automation industry since the late 90s when IEC 61158, created the fieldbus wars, more or less. And it's going to be the much needed peace treaty to the fieldbus wars. It's going to do a lot of really powerful things for automation as an industry. So, with the support of nearly every major automation supplier in the world, again, Rockwell, Siemens, Beckhoff, B&R, etc., Mitsubishi, Omron, etc., everybody. With the support of all of these huge players in the automation game, OPC UA TSN is going to be hitting the market really, really soon. I know from the B&R side, we've got products coming out within the next year or two that are going to have OPC UA TSN built in, and other vendors are having similar timelines. When that happens, the automation industry is going to start changing for the better, which is really, really good. So I myself, as an automation engineer, as a sales engineer, I'm looking forward to helping my customers implement this technology. I'm looking forward to testing out the products that we have at B&R that are going to use this technology. And I think it's going to bring a lot of value to a lot of not only OEM machine builders, but also the system integrators that have to deal with a lot of these communication protocols, and the end users that have to actually manage these machines, especially as time goes on and support kind of dwindles for older products. So OPC UA TSN is going to solve a lot of headaches that people every day are dealing with, and that's really powerful. So we're looking forward to that. If you have any questions about OPC UA TSN, I'm happy to answer them as best as I can. You can reach me at automationpodcast@gmail.com. The other way that you can reach me is directly on LinkedIn. So you can just search my name, Corey Dallas, and I'll be happy to connect with you and chat with you on LinkedIn as well. So in the future, we're going to be diving into some really exciting topics. The next episode, a little sneak peek, we're going to be looking at long stator linear motor track technology. This is another game changer for automation. So we're hitting the big ones up front. We're going to be talking about IIoT. We're going to be talking about web-based visualizations. We're going to be talking about cybersecurity, a lot of hot button issues. We'll talk about machine vision. So we're going to be hitting on some really cool topics that you should definitely stick around for. So if you do want to stick around for those, make sure you subscribe to the podcast on Apple Podcast or wherever you get your podcasts. Make sure you follow me on LinkedIn, get connected with me, as I'll be posting all of these on LinkedIn as well. And of course, if you see my post on LinkedIn, just go ahead and like that and share that for me. Thanks so much for listening to this episode, and we'll see you next time.